Hey guys, this is the second part of the video. Question 7a. Draw the circuit symbol for a potential divider. Make sure you're familiar with all the symbols for electric circuits. If you're not, you can take a screenshot of the screen right now. This is the circuit symbol of a potential divider. Next, question B. Figure 7.1 shows a circuit. Over here, you've got the EMF, which is 6 voltage. You've got a fixed resistor here, and this is a variable resistor. The difference between a variable resistor and a fixed resistor is that for a variable resistor, you can adjust the resistance to control the amount of current flow in the circuit. Question part 1. Calculate the value of V out when the value of R is 3 kilo ohms. So you're looking to find the voltage out when R equals to 3 kilo ohms. What you see here is two resistors that are being used as a potential divider. Most students find it difficult attempting questions on potential divider. However, the concept is actually pretty simple. Let's say I have a voltage in or the voltage supply of 9 voltage. And according to my resistor, if I have 2 ohms here and I have 1 ohm here, I am looking to divide my voltage to each of these resistors accordingly based on its ratio. So the ratio here is 2 to 1. So the voltage out here would be 6 voltage and the voltage out here would be 3 voltage. So you just need to split the voltage according to its ratio. So now let's look at this question. You've got 6 voltage here as your V in. One of the resistor is 1 kilo ohm and the other resistor is 3 kilo ohm. So the voltage is 1 to 3. So if I follow mathematical formula, this is how I'm going to do it. V out would be 1.5 voltage. And the other output would be 4.5 voltage. Or another way of solving this is by using the formula. The V in is our supply, so we're going to substitute 6 voltage over here. So R1 here would be the one which is parallel to V out over here. So the value is 1 kilo ohms over the total resistance of both the resistor, 1 plus 3. So rearranging this formula, I would get 1 over 4 times by 6 voltage, which is 1.5 voltage. The same value as here. Part 2. The value of R is adjusted until the current in the circuit is 1.7 milliamperes. Calculate the charge that flows through the circuit in 300 seconds. Whenever you are given with question to calculate, please list down all the information that you have in the question. You have the current and time and you're looking to find charge. There is a formula related to this which is Q equals to I times T. This is pretty straightforward. We're just going to substitute the value into our formula. When using this formula, you have to make sure that your current is in the standard unit of ampere. And right now it is milliampere. So we have to convert this. Milli is times 10 to the power of negative 3. So just put these values in your calculator and in two significant figures, your final answer would be 0.51 and the unit for charge is coulomb, capital C. Next, question 8 part 1. Figure 8.1 shows a wire carrying a large current. So as you can see here, the flow of current is going into the square card. Part 1. Figure 8.2 shows the square card viewed from above. The cross here is the image of the current entering in the card. When the current flows in, this is the symbol. And when the current is flowing out, you would see a dot. So on figure 8.2, draw 3 magnetic field lines that indicate the direction of the magnetic field and how its strength varies with distance from the wire. Okay, so let's look back at this diagram. To answer this, we need to use our right hand grip rule. When applying the right hand grip rule, the thumb will point at the direction of the current, and the curvature of the grip indicates the direction of the magnetic field. In this case, the current is pointing downwards, so your thumb should also be pointing downwards, like this. And you will notice that the curvature of your grip is this direction, meaning that the magnetic field will also be in this direction, which is clockwise. Okay, so now we're going to draw 3 circles in a clockwise direction. You also have to show how its strength varies with distance from the wire. To do this, we have to understand how current affects the magnetic field. The magnetic field is stronger when it is closer to the current, and as it moves further, the strength of the magnetic field will decrease. We can demonstrate the strength of a magnetic field by drawing the magnetic field lines closer to each other. And to demonstrate a weaker magnetic field, we will draw the magnetic field lines further from each other. So that's what we're going to do over here. As it moves further from the current, the magnetic field in this region would be weaker. Draw the lines further as it moves away from the current. Next, part 2. The current in the wire increases and the direction of the current is reversed. State how these changes affect the magnetic field. If I increase the current as mentioned, my magnetic field will also increase, meaning that the magnetic field lines will now be closer to each other. And as for the direction, if I change the current direction moving upwards, then now my thumb will be pointing upwards like this, and my curvature grip will be in anti-clockwise direction. So the magnetic field line will go on the opposite direction. So those are the changes that would affect the magnetic field. Question B. Electricity is transmitted at high voltage. Explain why a high voltage increases the efficiency of transmission even with thinner wires. Thinner wires have smaller cross-sectional area, meaning that it will have a higher resistance. And according to the formula of P equals to I times V, we know that if the voltage increases, the current must decrease for the same power. And we can use the formula of P equals to I squared times R to calculate power loss as heat energy. Therefore, reducing the current dramatically can reduce the power loss in the cables. Question 9, Part A. An experiment directs alpha particles at a very thin sheet of gold foil. Part 1. Most of the alpha particles pass through the thin foil in a straight line. State the conclusion about the atoms from this observation. I have explained in detail on this experiment in the Chapter 5 video which I have made previously. You can find the link to this video at the top of the screen right now. If you watch the video, you would understand that the particles mostly move in the straight lines, some are slightly deflected, and the remaining are deflected back. So the reason why the majority of them go straight through the gold foil is because the atom is mainly empty space. Next, Part 2. Some of the alpha particles are deflected through the angles less than 90 degrees and a few are deflected through 180 degrees. State and explain two conclusions about the nuclei of atoms from this observation. If it is deflected through a small angle, this is because the atom is positive alpha particles and they are repelled by positive nucleus. And if some of them are deflected back, this is because the nucleus is extremely small. Question B. A source contains a radioactive isotope of strontium. This isotope decays by emission of beta particles. The half-life of this isotope is 29 years. Part 1. State the change in the nucleus which occurs when a beta particle is emitted. When an isotope is unstable, it will go through radioactive decay, whereby it emits radiation such as alpha, beta, and gamma. And when a beta particle is being released during a radioactive decay, the neutron will turn into proton and electron. So you can say that the neutron is replaced by a proton. Next, Part 2. The initial mass of this isotope of strontium in the source is 25 microgram. Calculate the mass of the strontium isotope that decays in 87 years. Okay, first of all, check if this has any background radiation, and it doesn't. Let's find out how many half-life can the strontium go through. So the span of 87 years divided by one half-life, which is 27 years, we know that this isotope can go through 3 half-lives. So for the next step, we're going to halve the source by 3 times. So 25 microgram going through one half-life, it will become 12.5 microgram. Going through another half-life, it will be 6.25 microgram, and going through another half-life would be 3.125 microgram. So 1 half-life, 2 half-life, and 3 half-lives, which take a total of 87 years. Okay, so this is the final mass of strontium after 87 years. But pay attention here that they want to find what has decayed, not what is the final mass. So we're going to take the initial mass minus with what is left, which is 3.125 microgram. And from here we can find what is the mass that was decayed, which is 21.875 microgram. So in two significant figures, this would be 22. Question 10a. Figure 10.1 represents different positions A to H of the moon as it rotates around the Earth. Part 1. State a position of the moon where an observer on Earth sees a quarter moon and a full moon. The reason why we can see different phases of moon from the earth is because the light from the sun is being reflected from the moon's surface to the observer's eye in the earth. So depending on the position of the moon, we can see different phases and different shapes of the moon. Over here shows how the different position affects the phases of the moon. If the light directly hits the moon, we from the earth are able to see a full moon from this side. So a full moon can be observed at position G, and a quarter of the moon can be observed when the light hits this side. So we can see this side of the moon, and also at part E, when the light hits here, we can see the half of the moon. So for quarter moon, it's either A or E. Next question, part 2. State the approximate time taken for the moon to orbit the earth. This is something that you should know. The answer is 28 days, which is a month. Question B. The average distance of the earth from the sun is 1.5 times 10 to the power of 8 kilometers. Calculate the average orbital speed of the earth in kilometers per hour. The formula for orbital speed is V equals to 2 pi r over t. It mentions here that we are looking for the speed in kilometers per hour. That means the radius here, which is the distance, should be in kilometers, and the time here should be in hours. Put all these values in your calculator, and two significant figures, we would get 110,000, and the unit would be kilometers per hour. Part 2. The speed of light in a vacuum is 3 times 10 to the power of 8 meters per second. Calculate the time taken for light from the sun to reach the earth. So we are given with the speed, and we're looking to find the time. So the speed of light from the sun to reach the earth is 3 times 10 to the power of 8 meters per second, and we want to know how long this takes. We are already being given the distance here, which is 1.5 times 10 to the power of 8 kilometers. Just pay attention here that there is a unit conversion that has to be done, which is from kilometers to meter. So to find the time, we're going to use the formula of speed equals to distance over time. Rearranging this, we will get time equals to distance over velocity. Distance converted into meters would be 1.5 times 10 to the power of 11 meters over the velocity, which is the speed of light, 3 times 10 to the power of 8 meters per second. You will get approximately 500 seconds as the time. Question 11, part A. State the condition required for a protostar to become a stable star. For a protostar to turn into a main sequence, the inward force of gravitational attraction is balanced by an outward force due to the high temperature in the center of the star. Next, question B, part 1. Define the Hubble constant. Hubble law states that the further away a star is from the Earth, the faster it is moving away from Earth. So Hubble constant is actually the recession velocity to its distance. Part 2. The current estimate for Hubble constant is 2.2 times 10 to the power of negative 18 per second. State the equation which gives an estimate for the age of the universe. To estimate the age of the universe, we are going to use 1 over Hubble constant. So the equation would be 1 over h naught equals to distance over velocity. Part 3. Calculate an estimate for the age of the universe. To calculate the age of the universe, we will do 1 over Hubble constant, which is 2.2 times 10 to the power of negative 18, which gives us 4.5 times 10 to the power of 17, and the unit is seconds. That's all for this video, guys. Thank you for watching. For the next video, I'll be solving the Maths Paper 2. If you like this video and you found it helpful, please subscribe, like, and comment to my channel. Thank you. Bye. Take care.